This is the EdExcel A-Level Maths Paper 3, covering the Mechanics section, and it's from the 2021 series. Question number 1. A particle P moves with constant acceleration 2I minus 3j meters per second squared. At time t equals 0, P is moving with velocity 4I meters per second. For part A, we have to find the velocity of P at time t equals 2 seconds. For part A, we need to recognize we have constant acceleration. So, with constant acceleration, we would have to use the SUV equations. We need to find the velocity. We could use v equals u plus at. Let's write down what we know so far. We have u, which is equal to 4i. That's what's mentioned here. We have the acceleration, which is 2i minus 3j. We also have the time t equals 2. So, if we use v equals u plus a t, we are finding out what v is. That's equal to u, which is 4i. We add on to this the acceleration, 2i minus 3j, and then we will multiply this by t, which is 2. So therefore, v equals, 4i plus 2i times 2, that's 8i, and minus 3j times 2, that's minus 6j. So we can conclude v equals 8i minus 6j. Now for part B, at time t equals 0, the position vector of P relative to a fixed origin O is I plus j meters. We have to find the position vector of P relative to O at time t equals 3 seconds. Let's draw a quick diagram to help visualize what's going on. We have the position vector when t equals 0, the position vector when t equals 3, and then the resultant vector r is shown here. Now of course we are considering resultant vectors because we are finding the position vector of P relative to O. So the word relative to O would suggest we need a diagram like we see over here. So what do we know so far? Well, we know so far that t is equal to 3. We are also given that r0 is equal to I plus j. Let's find out r3. Now, of course, we'd have to use s equals ut plus a half at squared to help find out what r3 is. So, r3 is equal to u t plus 1/2 a t squared. So we've got r3 equals u, which is 4i, multiplied by t, which is 3, plus 1/2 times by a, which is 2i minus 3j, multiplied by t squared. So we will multiply by 3 squared, from which we can conclude R3 is equal to 21i minus 13.5 j. What we need to do is find out what R is. So R is equal to R0 plus R3 and so therefore if we work out what R is equal to R0, which is I plus j, and then we will add on to this R3, which is 21i minus 13.5 j. So therefore R is equal to 22i minus 12.5 j. Question number 2. A small stone A of mass 3m is attached to one end of a string. A small stone B of mass 3m is attached to the other end of the string. Initially, A is held at rest on a fixed, rough plane. The plane is inclined to the horizontal at an angle alpha, where tan alpha equals 3/4. The string passes over a pulley P that is fixed at the top of the plane. The part of the string from A to P is parallel to the line of greatest slope of the plane. Stone B hangs freely below P, as shown in figure 1. The coefficient of friction between A and the plane is a 6th. Stone A is released from rest and begins to move down the plane. The stones are modelled as particles. The pulley is modelled as being small and smooth. The string is modelled as being light and inextensible. Using the model for the motion of the system before B reaches the pulley, for part A, we have to write down an equation of motion for A. Well, if we know that tan alpha equals 3/4, we can use this information to find out what sin alpha and cos alpha are. Of course, through Pythagoras, the hypotenuse is 5, so sin alpha is 3/5, cos alpha is 4/5. Now, if we go back to the diagram, let's amend the diagram. What we know so far is when released, A moves down the slope. And if that's the situation, we know that the plane is rough. We have friction opposing it. We'll call this friction force F. And we also have the tension in the string. We'll call this tension T. And we've got the weight of A, 3 mg. So, with that, we can use Newton's second law to help set an equation of motion for A. With Newton's second law for part A, the sum of the forces is equal to the mass multiplied by the acceleration. The forward force will be 3 mg sine alpha. We've got the component here going forward, of course parallel to the plane. So we've got 3 mg sine alpha. We then subtract off f and we subtract t. And all of this is equal to 3 ma. We know sine alpha is 3/5. So we've got 3 mg multiplied by 3/5 minus f minus t. This is equal to 3 multiplied by m multiplied by a. And so therefore, we have 9 mg over 5 minus f minus t. This is equal to 3 ma. So what we have here is the equation of motion of A. Now, for part B, we have to show that the acceleration of A is 1/10 g. Now, before we do anything else, we can find out the resultant force R. If we work out the resultant force R, well, of course, that's equal to 3 mg times by the cosine of alpha. Of course, we are resolving perpendicular to the plane. So, for part B, perpendicular to the plane, we have R equals 3 mg multiplied by the cosine of alpha. We know cos alpha is equal to 4/5. So we have 3 mg multiplied by 4/5. And working this out, you will find R to equal 12 mg over 5. And going back here, we can find out what F is. So let's just write out what R is again, matching up the colours. R is equal to 12 mg over 5. F is equal to mu multiplied by R. So we have F, which is equal to 1/6. That's what mu is. Of course, we were told that the coefficient of friction is 1/6. And then we will multiply this by R, which is 12 mg over 5, from which we can conclude F is equal to 2 mg over 5. We can now find out what T is. Well, to find out what T is, we have T opposing A, and if B is moving up, the tension's helping B move up. We've got the weight of B resisting it. We've got the mass multiplied by gravity. And so if we resolve vertically, for the motion of B, we would have T equals mg, which of course is the motion of B. And if we substitute everything into the equation of motion for the entire system, of course, again, we'd have to use the sum of the forces equals mass times acceleration. So with the sum of the forces equaling the mass times by the acceleration, we have 9 mg over 5 we then subtract off F, which is 2 mg over 5. We then subtract T, which is mg, and this is equal to the mass of A, which is 3m, plus the mass of B, which is m, and don't forget, we multiply these by the accelerations. What we have here is the motion of the entire system. So, with the m's cancelling out, we have here 9 over 5 minus 2 over 5 minus 1 multiplied by g. This is equal to 4 multiplied by A. So if we work out the numerical value, 9 over 5 minus 2 over 5 minus 1, we have 2g over 5 equals 4a. Of course, A is equal to 1 over 10 multiplied by g, meters per second squared. For part C of the question, we have to sketch a velocity time graph for the motion of B from the instant when A is released from rest to the instant just before B reaches the pulley, explaining your answer. For part C, you can see here, we start off at the origin. The acceleration is constant, but the velocity will continue to increase. And so we see that the acceleration of B is constant. Now for part D, in reality, the string is not light. We have to state how this would affect the working in part B. Well, of course, with part B, we are finding the acceleration of A. Of course, here, the tension on A would be different to the tension on B. Question 3. A beam AB has mass m and length 2a. The beam rests in equilibrium with A on rough horizontal ground and with B against a smooth vertical wall. That's what we see here. The beam is inclined to the horizontal at an angle alpha, as shown in figure 2. The coefficient of friction between the beam and the ground is mu. The beam is modelled as a uniform rod resting in a vertical plane that is perpendicular to the wall. Using the model, for part A, we have to show that mu is greater or equal to 1/2 cot theta. Here we have a copy of the diagram. We've got the point A and the point B. Now, we have the weight of the ladder acting through the centre. We will add this on we have the weight of the ladder mg. We have the ladder, if it's on the point of slipping, the ladder will move like this, so friction will oppose it, hence the friction force is acting towards the wall. We'll call this friction force F. We've got the reaction between the ground and the ladder. We'll call this R. And then we've got the reaction between the ladder and the wall being N. So we will add this on over here. Let's now take moments about the point A. The reason we want to take moments about the point A is because we've got the most forces here, and so taking moments about A will eliminate those forces. If we take moments about A, we've got mg, the force, multiplied by the perpendicular length, which is A cos alpha. So we have mg multiplied by A cos theta, and this will equal N multiplied by 2A sine theta. Let's perhaps use the same colours used. We've got N, and here we've got mg. Let's now resolve horizontally and vertically. If we resolve vertically, we have R, which is equal to M multiplied by G. And if we resolve horizontally, we have F, which is equal to N. And so therefore, if we substitute everything in, we have mg, which we know is equal to R. We then multiply this by A cos theta, and this is equal to N, which we will leave alone for a minute. And then we multiply this by 2A sine theta. So we have RA cos theta equals 2NA sine theta. And if we solve for N, N is equal to R multiplied by A cos theta, and then we will divide this by 2A sine theta. So this is what N is equal to. And so therefore, recognizing that N is equal to F, We can therefore conclude f is equal to 1/2 multiplied by r multiplied by cot theta. Cos theta over sin theta is cot theta. What else can we mention? Well, we also know that f is less than or equal to mu multiplied by r, and knowing what f is, which is 1/2 r cot theta, this is less than or equal to mu multiplied by r, from which we can conclude mu is greater or equal to 1/2 cot theta. Now, a horizontal force of magnitude kmg, where k is a constant, is now applied to the beam at A. This force acts in a direction that is perpendicular to the wall and towards the wall. Given that tan theta is equal to 5/4 and mu is equal to 1/2, and the beam is now in limiting equilibrium, we have to use the model to find the value of k. Once again, we have the same diagram provided for us in the question. Let's add on some of the forces. The same as before, we've got mg here. We have r over here. Now, we need to be a bit careful. It's in limiting equilibrium. We also know from the question that a horizontal force of magnitude kmg is applied to the beam at A, and this acts in a direction that's perpendicular to the wall towards the wall. So we have a force going in this direction of magnitude kmg. So we're pushing the wall inwards. What's opposing it is a new frictional force over here. We'll call this new frictional force Q. And we've got the reaction at B. Say this has magnitude P. Now, what we need to do is find out what K is. How could we do that? Well, let's take moments about A. Same reason as before. The most forces are at A. Taking moments about A will eliminate those. So, we have mg multiplied by A cos theta, and this is equal to P multiplied by 2A sin theta. Now, if we resolve vertically, we have R equaling mg. R is equal to mg. And if we resolve horizontally, we have P plus Q, so let's just write this down. We have P plus Q equals KMG. So what we can do from this is rearrange to find out what P is. Now, before that, we know already from the question that we're in limiting equilibrium. And so if we are in limiting equilibrium, what we have here is Q which is equal to mu multiplied by R. So this is for limiting equilibrium. And so we have Q which is equal to mu, which we know is 1/2. So if we go back to the question, we know mu is equal to 1/2. And then we know what R is. That's mg. So Q is equal to 1/2 mg. And so therefore, if we consider the horizontal, we have P, which is equal to K mg minus Q, which we know is 1/2 multiplied by mg. So therefore, P is equal to K minus, rather here, we've got mg equaling R, so we've got KR minus 1/2 R as the value of P. So that's where this R comes from. And so if we substitute everything back into the equation here, we've got mg, which we now know is R. We then multiply this by A cos theta, and this is equal to P. Now, we know that P is equal to K multiplied by R minus 1/2 R. And then we have A sine theta. And don't forget, we still multiply this by 2. So what we can now do is find out what K is. To do this, let's first of all cancel the A's from both sides and divide through by cos theta. So we have r cos theta equals 2 lots of kr minus 1/2 r sine theta dividing through by cos theta. R is equal to 2 multiplied by kr minus 1/2 r sine theta over cos theta. R is equal to 2 multiplied by kr minus 1/2 r sine theta over cos theta is tan theta. We already know what tan theta is. We were told in the question tan theta is equal to 5/4. So we have r equals 2 multiplied by kr minus 1/2 r multiplied by 5/4. Of course, 5/4 is what tan theta is. Now, recognizing that 2 times 5/4 is 5/2, r is therefore equal to kr minus 1/2 r multiplied by 5/2. So r is equal to 5/2 kr minus 5/4 r. We can now find out what k is. K is equal to r plus 5/4 r divided by 5/2 r, and recognizing that the r's all cancel out, 1 plus 5/4 divided by 5/2, that's 9/10, which is 0.9. So therefore k is equal to 0.9. Question number 4. A small stone is projected with speed 65 meters per second from a point O at the top of a vertical cliff. Point O is 70 meters vertically above the point N, that's what we see here, and point N is on horizontal ground. The stone is projected at an angle alpha above the horizontal, where tan alpha equals 5/12. The stone hits the ground at the point A, as shown in figure 3. The stone is modelled as a particle moving freely under gravity. The acceleration due to gravity is modelled as having magnitude 10 meters per second squared. Part A. Using the model, we have to find the time taken for the stone to travel from O to A. Well, if we know that tan alpha is equal to 5/12, from this, using trigonometry, the hypotenuse is 13, and so sine alpha is 5/13, cos alpha is 12/13, and tan alpha is 5/12. Now, we need to use the constant acceleration formula. We need to use s equals ut plus 1/2 at squared. We're finding out the time. So, using s equals ut plus 1/2 at squared, s here is equal to minus 70. If we take this point to be the 0 level, then we have minus 70 as the distance. This is equal to u. Well, if we resolve vertically, of course, we have u, which is 65 sine alpha. We then multiply this by t. We then subtract off 1/2 multiplied by a, which is g, multiplied by t squared, minus 70 equals 65 multiplied by sine alpha, which is 5/13, multiplied by t, minus 1/2 times by 10, multiplied by t squared. If we rearrange, what we end up with, well, here we've got minus 5t squared, here we've got 25t, here we've got minus 70, so we've got 5t squared minus 25t minus 70. This is all equal to 0. We can use our calculator at this point to help us find the values of t. 5t squared minus 25t minus 70, t equals 7, t equals minus 2. And so with that, we can therefore conclude t equals 7. Of course, we take the positive value. So we've got t equals 7 seconds. Now, for part B, we have to find the speed of the stone at the instant just before it hits the ground at A. So what we're doing over here is finding out the speed. Of course, we would have to resolve horizontally and vertically. Now, we have to use the constant acceleration formula, v equals u plus at. So, if we use v equals u plus at, horizontally vh, that's equal to uh. Of course, there's no acceleration horizontally, so we've got 65 cos alpha, and we already know what cos alpha is. That's 12/13. So we've got 65 times by 12/13, which is equal to 60. Now, we can find out what the vertical is. That's equal to u vertical minus g multiplied by t. We have 65 times by sine alpha minus g, which is 10, multiplied by t, which is 7. So, we've got 65 multiplied by 5/13 minus 70. It turns out here we get minus 45. So in terms of the components, we have 60 and 45 here. Of course, minus indicates it's going down. What we need to do is find out the speed. So therefore, for the speed, we have v horizontal squared plus v vertical squared, all square rooted. V horizontal, that's 60, So we've got 60 squared, v vertical, that's minus 45. So we've got minus 45 squared. And if we work all of this out, square root of 60 squared plus 45 squared, that's equal to 75. The speed is 75 meters per second. Now for part C, we have to state one limitation of the model. One limitation of the model is that it ignores air resistance. We have to state one other limitation of the model that could affect the reliability of your answers. We know so far an approximate value of g has been used. In fact, we use g equals 10 meters per second squared. To make our answers more reliable, we could use g equals 9.8 meters per second squared. It's a more accurate value of g. Question number 5. At time t seconds, a particle p has velocity v meters per second, where v equals 3t to the power of 1/2 I minus 2tj, where t is greater than 0. For part A, we have to find the acceleration of p at time t seconds, where t is greater than 0. For part A, what we know so far is v equals 3t to the power of 1/2 I minus 2t j. So, acceleration is equal to the differential of velocity. We would have to differentiate the velocity 3t to the power of 1/2 I minus 2t j. And if we differentiating 3t to the power of 1/2, we end up with 3/2 t to the power of 1/2 minus 1, which is 3/2 t to the power of minus 1/2. And if I differentiate minus 2t, we end up with minus 2. This is in the direction. And of course the units, meters per second squared. Now we have to find the value of t at the instant when p is moving in the direction of I minus j. Here we have a quick diagram. I is in the direction of east, north is in the direction of j. I minus j, which is what we see here, is in the direction of southeast. Southeast. And so therefore, what we can conclude from here, with southeast, I is equal to minus j. So if we take a look at what's mentioned in the question, we're moving in this direction here. So we need to consider the velocity vector. The I component is equal to the negative of the j component. The I component is 3t to the power of 1/2. And the j component, that's minus 2t. So what we have here is 3t to the power of 1/2 is equal to minus 2t. What we need to do is find out what t is. That's what the question specifies. So we've got 3t to the power of 1/2 equals 2t. If we rearrange, we've got 3/2 equals t over t to the power of 1/2. 3 over 2 is equal to t to the power of 1/2. Of course, t divided by t to the half is just t to the half. And if we square both sides, we can conclude t is equal to 9 over 4 seconds. For part C of the question, at time t seconds where t is greater than 0, the position vector of p relative to a fixed origin, or, is r meters. When t equals 1, r is equal to minus j. We have to find an expression for r in terms of t. Well, for part C, we need to recognize r is equal to the integral of v with respect to time. We know what v is. V is 3t to the power of 1/2 I minus 2t j. So we need to integrate the result we see here. Integrating 3t to the power of 1/2, we end up with 2t to the power of 3 over 2 in the I direction, and in the j direction, integrating 2t, we end up with t squared. And we've got a constant of integration, which we'll call c. Now, we also know when t equals 1, r is equal to minus j. So we've got minus j equals 2 lots of 1 to the power of 3 over 2 I minus 1 squared in the j direction plus c. So we've got minus j equals 2i minus j plus c. Of course, the minus j's cancel on both sides, and if we rearrange for c, we can conclude c is equal to minus 2i. And knowing that c is equal to minus 2i, replacing c with minus 2i, we can therefore conclude the position vector r is equal to 2t to the power of 3 over 2 I minus t squared j minus 2i, which is what c is. And if we want, we can gather all of the I components together. So we've got 2t to the power of 3 over 2 minus 2i, and then we've got minus t squared j. Don't forget the units of meters. For part D of the question, we need to find the exact distance of p from O at the instant when p is moving with speed 10 meters per second. Now, we already know what v is. The magnitude of v is of course equal to 10. So, the magnitude of v is equal to 10. So we've got 3t to the power of 1/2 squared plus minus 2t squared, all square rooted. This is equal to 10. And if we square both sides, we've got 3t to the power of 1/2 squared plus minus 2t squared. This is equal to 10 squared. 3t to the power of 1/2 squared. Well, we've got the 3 which is being squared, that's 9. We've got t to the half being squared, so we've got 9t for this result. Minus 2t all squared, that's 4t all squared, and that's equal to 100. Rearranging, 4t squared plus 9t minus 100 equals 0. we can again use our calculator to find the value of t. The value of t, that will be 4 and minus 25 over 4. And of course, because t is greater than 0, we can therefore conclude t is equal to 4 seconds. And knowing that t is equal to 4 seconds, what we need to do is find out, going back to the question, the exact distance. Before we find the exact distance, we can use what we found here to find the position vector. So, with t equaling 4, r is equal to 2 lots of 4 to the power of 3 over 2 minus 2 in the I direction, and in the j direction we've got minus 4 squared. So if we work out what r is, we've got 2 times by 4 to the power of 3 over 2 minus 2. So it turns out here we get 14i, and then we've got minus 16j. What we need to do is find out the exact distance. The exact distance is equal to the magnitude of r. So we've got 14 squared plus minus 16 squared, all square rooted. 14 squared plus 16 squared, square rooted, is 2 times by the square root of 113. Don't forget the units of meters. Now, because it said exact distance, we don't need to round this to 3 significant figures. So the exact distance is 2 root 113 meters.